So as you can see, we're going old school today and doing this on a whiteboard. My name is Tal Perry. So you would have seen cool stuff about me, but roughly, I just moved today to Berlin from Tel Aviv. I work at Citibank, big bank, lots of people, lots of problems in NLP. We had problems with everything Miroslav said. So I think the biggest takeaway you should take from the talk is do everything that he said, because he's absolutely right. And once you get that right, you can start thinking about fancy algorithms, which is what I'm going to talk about. So a bit about like what I do or what I've been doing for the last year is roughly looking at chat data, which is just as horrible as the medical text that Miro showed us. It has emojis and crappy spelling, and the guys that are writing it are more interested in making money than like actually writing proper English. And then we need to extract stuff from this. So one of the solutions we came up with was we're going to work at the character level instead of the word level. And this has a really big plus in that it solves all of those terrible problems. And a really big minus, which is it makes your sequence like 5 or 6 times longer. So the amount of processing you need to do is longer, and everything's slow. And I'm very impatient, and so I started looking for solutions. And this is what this talk is about. So now the next slide that you're not seeing is the punchline, okay? So the punchline for this whole talk is, and my handwriting is terrible, please excuse me, but convolutions, okay, are fast, okay? And if you take away one thing from this whole talk, is that using convolutions will usually be much faster than using what we usually use in text and deep learning, which is RNNs, okay? So I'll define all these terms. If I'm talking a bit of Chinese, I'll eventually go down and define everything. But kind of why is fast important? So fast is always nice for the user, but in kind of deep learning and machine learning, we have 2 places where speed is really important. One is when we're iterating, right? When we're doing research, if we can run our pipeline in, I don't know, an hour instead of a day, that's really nice, because we can iterate much faster. And we can reach results or find problems or resolve things or just be more creative, because things are going much faster. The other thing is in production, right? If you take a big model and it's really heavy, and it's doing tons of compute, and you need a big GPU or a cluster, that shit's expensive to put in production, right? So you need to get these big Amazon machines, or you need to buy the hardware locally, and you need to make sure everything's configured, and it's a big pain in the butt. So it's much nicer if you can take a model and just dump it on a simple quad-core machine with basic RAM, like something dumb and commodity, and run with that. It just makes things cheaper to put in production and easier and to guarantee certain SLAs. So kind of the nice thing about this slide that you're not seeing is, there's this famous Venn diagram that's like, right, good. I don't know if you can see this. Cheap, right, and fast. And, they always say it's like the CAP theorem, good, cheap, fast, choose 2. So my claim here, so-called, is that with convolutions, you can get good. I mean, you'll get results that are pretty good for most tasks. You'll get cheap in terms of the amount of effort you need to put in and the hardware that you need to use to deploy it in production. And you'll get fast. These things are really fucking fast, which is awesome. Pardon my French. Great. So what are we going to cover today? I'll briefly just go over common tasks in NLP, and again, I wish I had my slides, but never mind. We'll go over what does a convolution look like? What the hell is this thing? And then a bit of technical requirements, or any system where we're working with text, kind of what we want from it. And we'll go from there. But let me stop here for a moment, and let's make this a bit more interactive. So raise your hands if you want to know what an RNN is. Wonderful. OK. Raise your hand if you've put a Tensorflow in production before. OK, good. So an even mix, so I can't focus on this for that. Great. So let's do this. I'm going to talk, and if you guys have questions in the middle, raise your hands, and I'll repeat them, right? I know everything I want to say. If it's not clear to you, stop me and ask so that we're all on the same page. Great, let's go. So things we want to do in NLP. Okay, so one of the big things that we got last year was translation, right? Google published this amazing system where it can translate from a bunch of languages, and they trained it to do English to Chinese and Chinese to Korean, and then kind of magically they got a system that can do English to Korean. So that's a really, really big breakthrough, right? It's been one of the big problems in NLP, and it opens up a bunch of things. Other stuff we want to do, speech recognition, right? So we all talk to our phone now and go like, Siri, you know, where's my lunch? Or OK, Google, whatever. So that's huge. That's something new. It's in the domain of language processing. A lot of times we want to do sentiment analysis, right? So we want to understand, you know, are people talking about a particular stock and do they think it's going to go up? Or do people like this product? Or are people talking trash about me on social media? So all that is taking text and somehow trying to reduce it into positive or negative, right? What else do we want to do? So, I don't know, dependency parsing is boring. And I prepared, pictures, but you can all imagine, right? We all text, right? We all use WhatsApp or Facebook Messenger or whatever, and it has this terrible autocomplete. Oh!
Okay, all yours.
All right, amazing. All right, so I was saying, wait. Well, why are you laughing? Did I put something there I shouldn't have? Great. Okay. So, as I was saying, right, so we have all of it. So, I don't know, I would write to my girlfriend, I love you, and she'll write back, totally over you. And then, shit, that's the autocomplete, fucked it up, right? And the thing is, what was it trying to do, right? Well, if you think about it, what is the system doing? This is going to be on YouTube. Wonderful. OK, so what is this autocomplete trying to do, right? It's looking at the sequence of characters I inputted, and it's trying to predict what's the most logical thing that I'm about to say so that I don't have to write it. And if it was smart, it would look at the context. Like it would say, the girlfriend says, I love you, I totally over you is not the right answer, almost in any context. So this is a big fail. And why is this stuff hard, right? If you think about it, like English, technically, or language in general, it has rules. We studied them in school. There's grammar, and there's, I don't know, spelling, and the things make sense, but they're ambiguous. They get really complicated really fast, and it's hard to map them out algorithmically. But that doesn't even matter, because in reality, no one follows the rules, right? I've probably made 100 grammatical mistakes since I've started this talk. So even if we map the rules perfectly, they're just not relevant to natural language because we don't follow them. They don't matter. And finally, all data is dirty. So I think Miro made a good case of pointing that out. But you know, we always collect data. If it's audio, it's dirty. If it's text, people are doing spelling mistakes and whatnot. So it's hard to trust it. But as NLP practitioners, when we want to do all these things in text, we need to solve those problems, right? It's not an excuse for not solving the problem. It's just another challenge we need to get through. Don't do that. OK, so now let's get into the bread and butter of things, OK? Convolution. So who here knows what a convolution is? Just help me out. This is wonderful. OK, so most of you. So for those of you who don't, basically think of a convolution as like a sliding window. It's like an n-gram, right? So I want to look at, say, I think I have 3 words here. Love my new, right? So that's like a convolution of width 3, right? I'm looking at 3 words at a time, and I'm going to slide this box over kind of to the next 3 words and the next 3 words, and then each time I'm convolving. I'm doing this operation, OK? So what is this convolving? If you think about it, like, we can represent words in all sorts of ways. And in this case, we're representing them as word vectors. So like word to vec and glove and all that stuff, right? And then you get exactly this. You get this kind of box where the x-axis is the words, and the y-axis is all the different embedding dimensions. So I don't know, we'll embed it to 50 dimensions or 300 dimensions. We'll go over that. And then each time, we're going to take this convolution thingy, and it's going to look over all the vectors from the 3 words and kind of do some linear operation on them and combine them and reduce them into a single number, right? And then when we slide over, when we go from love my new iPhone to, I don't know, my new iPhone, then we'll fill in this box. And then when we go one more to the right, we'll fill in this box, right? Each time with a number. And we use the same. So the convolution thingy, this blue thing, this is a sequence of numbers. It's the linear operator. So basically, it's a matrix, right? And when we're learning in deep learning, what we're learning is the numbers inside of the blue thing. And then we keep on using them again and again as we slide over our input text. And again, we slide over, we fill this guy in here with a bunch of different numbers, all with the same filter. But the thing is, we want more than one, right? So that's basically learning a feature for every n-gram, every 3 or 4, whatever we define. But what we can do quite easily is just do this again and again and again and again with a bunch of different filters, with different matrices that we're learning. And that's what you're seeing kind of stacked back here. So each one of these kind of corresponds to, each one of these columns corresponds to a different set of features that I learned over the same words. So I can keep generating these kind of deeper and deeper, or richer and richer sets of features over my same inputs. That's convolution. Does that make sense? No? Good. Come to me later, because you're the only one. All right. So if we think in general of an NLP system, like when we're looking at text, we have 2 requirements that we want out of it. One is it can handle arbitrary input lengths, right? So if I say, hi, I'm Tal, that's a sentence with 3 words. And if I say, hi, I'm Tal, and I just came here from Tel Aviv, and now I'm looking for an apartment in Berlin, then it didn't count, but that's many more words. But we want our system to be able to take the short sentence and the long sentence and be able to hold them both, okay? And the classical way we do this is with the bag of words approach, right? Where we just count words, basically. And then we kind of have this big table. This word appeared, this word didn't appear. But that doesn't give us anything about the relationships with the words. So the second thing we want from any NLP system is to be able to capture dependencies at local scale, at different scales, right? So if I'm saying, hi, I'm Tal, so you want to know that am and I are referring to me. And if I'm talking at this very long sentence, then at the end, when I said Berlin before, you want to know that the Berlin is somehow referring to the I that is Tal that is looking for something, right? So within any given piece of text that's arbitrarily long, there are dependencies at different scales, and we want to be able to capture most of them. So I'm sure that didn't make too much sense. So let me give you an example, okay? So this is a cool picture from OpenAI. OpenAI is a research group in San Francisco, and they built this crazy network, right? And all they had to do, they fed it Amazon reviews, and every time they gave it one character from the review, and they asked it to predict the next character. And then they gave it one character in the review, and they asked it to predict the next character. And they trained this thing on all the Amazon reviews they could get their hands on, and they ran it for like a month on 1 billion GPUs and crazy sizes and memory, like something nuts. And then they said, hey, can we like actually learn sentiment from this, right? So once we run this thing on a review, we get some sort of vector. We'll talk about that more in a minute. And can we predict sentiment from it? And it turns out that, wow, shit, we can, and we can even do it at the character level. So this particular review is interesting because it's talking about a movie adaptation for a book. So in the beginning, she's like, this is one of Crichton's best books, okay? And we'll see best book, and every one of us, just like the algorithm, is going to say, oh my God, sentiment is amazing. And then the writer keeps on going and saying that how great the book is, but how terrible the film is, and how like they did a really bad job at adapting it. But then what's really amazing is down here, if you look, all right? So it says, the book is really, really good. Now, any kind of classical NLP system that I know of will see really, really good, and it's going to shout out sentiment super positive, right? But this guy didn't, all right? It somehow managed to remember that even though the really, really good is talking about the book, the object of the sentence isn't the book, it's the film. And so the sentiment didn't jump up. And that's kind of an example of a very long-term dependencies at multiple scales within a text. Does that make sense? Great. So, sure.
Don't you think that it just learned that book and really, really good in a sentence is just a bad thing to say in an Amazon review about a movie?
Excuse me? Say it again?
Really, really good book is generally a bad thing to say when talking about a movie.
It could be, but then it still knows that it's talking about a movie. So, right, it captured that, but it still remembers I'm talking about a movie, even though that's like, we recognized the movie 3 sentences ago. And that's the long-term dependency. Okay? Okay.
Also, many movies would say, this is a really great movie based on a really, really good book. So there's no way.
Yeah. All right, so some of you before said you'd like to know a bit about RNNs, so let's do that. Okay, so RNNs, recurrent neural networks, and their modifications, LSTMs, these have become like the shit for deep learning on text, right? So all of our cutting edge stuff in translation, in speech recognition, in sentiment, in word imputation, and whatever like NLP task you have on a sequence, you know, the state-of-the-art solution and the stuff that's in production that we're all using on our phones, LSTMs or RNNs, okay? So basically what they do, so the RNN is this box A, right? And we feed it inputs, right? Don't do that. Help me. You'll live with this. If someone wants to come and help me make it nicer, that's great. If not, don't. All right, so we have this box A, and what A does is we feed it an input, like hi, go away. Hi, yeah, so hi, I am Tal, right? And we feed into this box A. And every time we feed it an input, it gives us an output. That's great. But the beauty of this thing, A, is that it's a state machine, right? So when I feed it hi, it remembers that it saw hi. And when it gives me the output for the next word, I, then the output's gonna be conditioned not just on the input I gave it, I, but also on everything else that it saw before, okay? So if I give it a really long sentence or a full paragraph like we saw that, it's gonna condition every output, even 3,000 or 4,000 words down, on the previous inputs that it saw. And in that sense, it's very much a state machine. But what's kind of nice about it is that it's a distributed state machine. So instead of having like a finite list of states in the transition and a discrete transition system, it's all distributed, right? So it's very soft, and we can go into subtle directions, and it's very hard to interpret. But it allows for a very rich expression of anything, right? Of states. And let's take a quick look at how this thing looks in Python. So this is the actual implementation for a recurrent neural network. You can copy paste this stuff like I did and run it, and you'll have something that will actually do the inference step. It still doesn't learn, but it goes forward, right? So basically, the RNN, it has three pieces that learn, that like we're training. So it has a matrix that learns the transition from hidden state to hidden state. So like my internal state now is I saw nothing, I saw the word I, and there's a certain transition from my first state to my next state. How do I transition given one input? How do I transition? How does it influence my own state? All right, that's another matrix. And finally, given the state that I'm in, where my box A is in, what output should I put out? Okay, and these are the three parameters that the RNN is learning, and it of course contains a hidden state. And then at every step, every time we go away, every time we give it an input x, it takes the dot product, the matrix product between this vector of our input and our transition matrix. It adds it to the dot product of our state and the transition matrix for states. It applies a nonlinearity, and that's it. And that's our new state. Okay, and then for the output, we just take our new state. We use the other matrix that we have, and that's the output, right? That's it. That's what it does. So I don't know if that sounded simple or not. If you spend a few minutes with the code, it is. All right, so what's nice about this thing? It takes inputs, which is great. It arbitrarily, as long as we want. Right, we can do I am Tal, and that will work here, and we can put in a book, and that'll work here. And it captures long-term dependencies, exactly what we wanted. Great. And then we can do things that are crazy. So this is like an example of how we originally did translation with RNNs. So the first paper, sequence-to-sequence learning by Ilya Sutskever, I think it was in like 2014. He said, all right, we'll take an input in English, we'll run the whole thing, and then we'll take this vector h, and we'll just dump it into a new RNN, and we'll let it output something, feed it back into it, output something, feed it back into it, and that's how we're going to translate. And he showed, wow, shit, this stuff works better than anything we've ever had before. And then things got crazy quite quickly. So they're like, well, we're only going from left to right, but sometimes we also want to have the context at the end of the sentence influence the beginning. So let's set up something like this that goes left to right, and another one that goes right to left, and we'll stack them together. And then we can get the context from both sides. And then I'm going to skip this one, but it gets pretty bad. Great. Oh, thank you. So remember a few minutes ago I told you that LSTMs or RNNs, they're the state of the art in everything we're doing in NLP, right? This is what we have in production. So why do we even want to talk about convolutions, right, if we have this great solution? And here's one answer for you, all right? So this is Mallory, the first guy that climbed the Everest. And why did he climb the Everest? And he said, it was there. And it's not just a smart-ass funny answer. I think that the world of deep learning, machine learning, and data science, it's really exploding now, and there are a lot of new things to play around with. And a lot of us, especially if it's our job, we have the luxury of getting to explore new and interesting things. And once in a while, a lot of times it's going to be time kind of wasted or without much ROI, but once in a while you'll stumble upon something that's really interesting or really practical or really helps your work or really helps you understand what you're doing. And I think just for that reason, it's very worthwhile to pursue these things that are maybe not intuitive, not common. But if that doesn't convince you, then the more important factor is that convolutions are just really, really fast and data efficient. And the reason they're really, really fast is that they work in parallel as opposed to RNNs that work sequentially. So what do I mean? I'll go back for a second. So look here, right? We can't process if this is like I am Tal. Damn that thing. Go away. All right, so if that's I am Tal, so we can't process Tal, right, before we processed I am. So we're working sequentially here. But there's no parallelism, and we definitely don't get to leverage the kind of inherent parallelism of GPUs, which is what everyone's talking about. There's a very big bottleneck. Conversely, with convolutions, so we can run this filter and the filter after it and the filter after it at the same time, all right? So we can, because there's no dependence between them. They're just these really small, tiny operations. And it just so happens that GPUs are very, very good at running these kinds of computations in parallel. And just for that reason, you get this tremendous speed up. Just because in this case, the computation runs in parallel, and in RNNs, the computation is sequential. It's a big deal. Great. So they work in parallel, make better use of GPUs. Another nice feature, so I showed you a few minutes ago that the RNNs, if we want to take the context that's coming from the end of the sentence, like, hi, I am Tal, and you want to know that, you want to somehow output something about hi that takes Tal into account, we need to make a pass from left to right and a pass from right to left. So we have to double our computations to get both sides of the sentence. Conversely, convolutions, we'll look about in a minute, they work hierarchically. So we'll do one layer of convolutions of trigams, and then we'll do another layer of convolutions on top of that, and on top of that, and on top of that. And each layer will kind of look at more and more of the input, but it'll have some view of all of it. And that's going to give us kind of a hierarchical understanding of our inputs. And I'll show you an example of that in a moment. And just to tell you that I'm not making this stuff up, and that someone certified kind of says the same. So Facebook published an article about a month ago where they showed that they got an improvement, 1.5 blue improvement over a very well-performing LSTM-based translation system, and their thing is 9 times faster than the baseline they compared it to, right? And Google just published an article like that as well, and so this is stuff, it's not just me saying it. Great. I am going to skip this part. Does anyone have a strong desire to see how to write the code for a convolution? Yes? Excuse me? First of all, that's not true. And second, I'm going to show you how to get over that. OK, so the man makes a point. OK, so I have 10 minutes. OK, all right, so let's skip it. And whoever buys me a beer, I'll show them how to do it. But just because you said it, there is now one-dimensional convolutions in Tensorflow. And here's how to, if you need to do other operations that aren't supported in 1D, so the slides that are on GitHub have the way to do it and get around it. And that's great. But here's, I think, the most important conceptual thing that I want to pass on. Okay, so there are two kind of parallel concepts when we talk about convolutions. One is receptive fields, and one is hierarchy. Okay, so let's start with hierarchy, and let's look at the example of images. Right. So Facebook is really creepy. They always know that it's me when I put up my picture. Right. because they can do facial recognition. And how do they do that stuff, right? So they get an image, and they do these layers of convolutions on them. And the first layer, some of you have probably seen this, learns like really basic features, like little edges and curves and kind of differences in brightness or whatever. And then the next layer looks at a bunch of these guys together, and it starts to put together like more advanced shapes, like an eye, a nose, a mouth, or whatever. And then the next layer on top of that, it's looking at noses and eyes and whatever, and eventually it's putting together a whole face. And from that face, then it can figure out this is Tal, this is not Tal, hot dog, not hot dog, stuff like that, right? But think about it, like how many pixels are involved in seeing a face, or how many of these guys are involved in seeing a face? So a lot. So when we say receptive field, what we're talking about is that the final layer in the convolutional network, so maybe this guy here, how many of the original input pixels, or in our world of text, how many of the original words or characters is it able to see? And that's the receptive field, okay? And so we can make the receptive field bigger in a few ways. We can make the convolution at each step wider, right? Before I showed you like step 3, but we could do step 100 or step 150, and there are trade-offs, right? We'll pay a big performance, we'll pay a computational cost, but it'll work. Or we can do what we're doing here, and we can kind of stack things up. So if you look at like, hey, this guy is seeing, this guy is seeing 2 inputs, right? And then this B guy is seeing 2 A's, okay? And each A is seeing 2 inputs. One of them is shared, so each B has a receptive field of 3. And then we could keep going and get a receptive field of 5 and 10 and 20. We can just keep on stacking them. And this is kind of important. So I want everyone to take a moment and tell me what you think of this sentence. No one? Really? Huh? OK, so I'm going to point out to you, it's not a question, right? There's a period here. OK, so it's not what has 4 letters. Like, it's not asking this, what has 4 letters? 1, 2, 3, 4. Sometimes has 9 letters, right? Never has 5 letters. Great. And this is a valid English text, but it confuses the hell out of us because we read the word what and we assume it's a question, even though we have a period at the very end of it that completely changes the meaning of the entire sentence. And the kind of point is, when we think about us as people or a system, we want to be able to get everything into the receptive field. So a lot of times we can't answer the question before we saw the entire input, and we can't say something about the first word or the first character before we see the last one, because it can change the entire meaning of everything. Okay? So when I'm talking about receptive fields and why they're important, because in text we always and every time I've worked with text, I've always wanted to get the receptive field as big as I possibly can. How much time do I have left?
Like 5, 6 minutes.
All right. Well, I'm gonna run through this. Okay. So the thing is that it's really hard to make the receptive field big. Okay, it's just not trivial. The trivial way is to kind of stack the convolutions, one layer on top of another layer, and intuitively this should work. But the thing is, right, so when you go forward, when you make the inference and you pass it through all these layers, then it does work, right? Like, there's no problem. But on the way back, when you're learning, when you're doing back propagation, deep learning or whatever it is, the signal needs to come back through these layers, right? And at every step, if you've got 100 layers that went forward, the gradient, the signal, the way to correct things has to go back 100 layers. And a lot of times in those 100 layers, it's going to end up getting multiplied by really small numbers. And if you take a lot of small numbers and you multiply them by each other, you're going to get 0. And then you're going to feel like that. Because when you get 0 in your gradients, then your network's not going to learn anything. You're just going to run it for 3 days, and nothing's going to happen. And again, you'll feel like that. And swear to God, I felt like that. But there are 2 solutions, and I'm going to really quickly run through one of them with you. I like both of them, but the one we'll talk about in a second, as I've had so much success with it recently that I love it so much, and I highly recommend you all embrace it. So what we're going to talk about is residual connections, and I'll explain that in a second. And there's another cool trick called dilated convolutions, which is if any of you saw like WaveNet and ByteNet, like these Google papers where they like learn to play the piano or generate crazy sounds, so they use that trick, but we're not going to talk about it. So let's go right into residual connections. Thank you. All right. So here's the shtick, right? We said with convolutions, if we naively stack them, then the system, like the signal has, this is like stacked convolutions, right? Each one of these colors is a layer. And in the traditional way, the only like connection is the straight line between them, right? So the obvious thing to do is kind of to put a line, some sort of way for the signal to go directly from the first layer to the last layer, from every layer in between, right? And there are a few ways to do this. 2016 was like the big year of residual connections, right? And the coolest, and the one I like the most, is comes from a paper called DenseNet. And basically what they say was, you take the output of your first layer, of your layer, and then you run it through a convolution, and you concatenate the two outputs. So I don't know if that made sense. Luckily, I have a picture now that we have this thing, right? So we start with our initial text. We run a convolution on it. Maybe we had the initial representation of the text was like each word was a three-dimensional vector, right? And then we ran a convolution on it, and we got 24. The output was a 24-dimensional vector. So we start with that. Now we have our 24-dimensional convolutions. We run another convolution. This time that outputs 12. And now instead of just keeping those last 12, what we're going to do is concatenate them. So on our next step, we're not going to have 24. We're not going to have 12. We're going to have 36. We're going to have the 24 from the previous step and the 12 we just calculated. And that gives us this first line here, right? The 24 that we just took out and the 12 that we calculated. And then we can do that again, right? We'll calculate another 12 features. And instead of just keeping them, we'll concatenate them. And again, and then we get 48. And what this does is give us direct connections, so our gradients can always travel directly, but it also gives us something else that's really nice, right? So traditionally, when we use convolutions and we take just the upper layer, we have a view of the original input, but it's kind of fuzzy because we're looking at all these different abstractions that we learned. But this way, we're also preserving every abstraction, every layer together. So we can look at directly at the original input. We can look at like its trigram, we can look at the trigram of the trigram, et cetera, et cetera. And so I'll give you, I think this is my last slide. So just kind of from my personal experience, how nice this has been for me. So I put a system recently in production, work. I built it originally with an LSTM, eventually with convolutions. And we got to the point where we got equal results with both systems, but the LSTM system took 2 days to train, had 1 million parameters in it, and was slow in production. And the convolutional system had 80,000 parameters instead of 1 million, and would train in about an hour. So that was a great success, and essentially based on this architecture. And that's it. Thank you.